Hello everyone. This video goes over the Unit 1 practice exam for Physics 252. Number 1, the graph below is a snapshot of a wave traveling toward the right at a speed of 100 meters per second at t is equal to 0 seconds. Write an equation for the displacement of this wave. So we can start with making two measurements off of this graph. One is going to be the amplitude, which is just the distance from 0 to either the highest point on this wave or the lowest point. And because it's a distance, that means it's a magnitude. That means that it's going to be something that we can always express as a positive, even if we were going to measure it from 0 down to the negative. But no matter which choice you make, you're going to end up with the same value, 0.04 meters. And then next, I can measure the wavelength. That is the distance from peak to peak. I could measure it from trough to trough. And another position or another way that I could measure it with this particular graph is to start right here. So where the graph intersects with the y-axis, and then move through that wave until I get back to that same position after one complete cycle. So measuring from there, I can trace down, I see that this is 1.5 meters. That's the same value as you would get if you estimated the positions of the troughs or the peaks. So I'm going to write that wavelength as a fraction. 1.5 meters is 3/2 of a meter. The wave number, k, is just going to be 2 pi radian divided by that wavelength. So that leaves me with 4 pi over 3 radian. And in the denominator, I still have meters. So this is radian per meter, technically. And now that I know that, I can use omega is equal to v times k to figure out what the angular frequency is in radian per second. That is 100 meters per second times 4 pi over 3 radian per meter. The meters cancel. We have 400 pi over 3 radian per second. Now, bear in mind, if you had centimeters on this axis on the horizontal, you could have come up with a different wave number because your wavelength would be different. However, omega is going to be the same value, regardless of whether you determine this in centimeters or meters. So now that we've got those two, we can figure out what the phase constant is. That's the last unknown here. And the way that we can determine that for a graph that neither starts with the minimum at x is equal to 0, nor the maximum, nor 0, but I'm somewhere in between, I can just take a look at the initial conditions. So on this graph, at t is equal to 0 seconds, x is equal to negative 0.02 meters. And this x is a reference to the displacement axis right here. So the displacement when x is equal to 0 and t is equal to 0 is that negative 0.02 meters. And I know that's equal to a times the sine of kx minus omega t plus phi naught. And I know it's minus because we were told that this wave propagates toward the right. If this wave were propagating toward the left, we would put a positive sign in there. So I've got the displacement at x is equal to 0 and t is equal to 0. I'm going to plug in an x is equal to 0 inside the sine function, and then also a t is equal to 0 inside the sine function. And everything except for that phi naught is going to cancel. So that means I can solve for it. I have 1/2 or negative 1/2 is equal to sine of the phase constant, phi naught. And I can take an inverse sine to figure out what that is. And you end up with a phi naught, an angle, phase constant phi naught, that's equal to negative pi over 6 radian. So the complete displacement function for this wave is going to be D is a function of both x and t because we can't localize that wave at one point in space, nor can we localize it at one point in time. It's equal to 0.04 meters times the sine of 4 pi over 3 radian per meter multiplied by x minus 400 pi over 3 radian per second multiplied by t minus pi over 6 radian. A 2.0 meter, 24 gram string is stretched to a tension of 25 newtons. What's the wavelength of a 230 hertz wave on this string? So the fact that I know the mass, the length, and the tension of the string means that I can calculate the wave speed without ever examining this 230 hertz wave. That wave speed is just going to be the string tension divided by the linear density, mu, where the linear density is just the mass of the string divided by its length. And I need this to be in kilograms per meter because I need this to cancel out a kilogram and a meter that show up in the Newton. So 24 times 10 to the negative 3 kilograms divided by 2.0 meters leaves me with 1.2 times 10 to the negative 2 kilograms per meter. I can plug that into the denominator of the expression that's up here in the top line, along with the 25 Newton tension, and I get 45.64 meters per second for the wave speed. That means that any wave of any frequency that propagates on that string is going to have that same speed. But of course, the frequency of the wave is going to impact the wavelength that you observe. So I can find that wavelength just by taking the speed divided by the frequency. So I get 0.198 meters, which I can round to 2 sig figs. That is 0.20 meters. Number 3, without resetting the frequency, what tension would produce a wave with a 0.460 meter wavelength? I have the same string, the same everything, so I know the wave speed. I have, the same string, so the same linear density, but a different tension. I apologize. So I can take the wavelength I was given with the original frequency because we know that it's the same, and I get a new wave speed of 105.8 meters per second. And now I can just backtrack and use the wave speed expression that we used first when we were solving number 2. I can rearrange this to solve for the string tension, and that's going to be the square of the speed times the linear density, and the linear density is no different than it was before. And now I find that it would require 130 newtons of tension in order to produce a 0.460 meter wave at 230 hertz. Number 4, what are the wavelength and frequency of an m is equal to 1 standing wave on the same string at the original tension value? So we're reverting back to the original speed of 45.64 meters per second. And because this is a standing wave on a string, the only way that standing waves will fit on that string is if there are nodes on either end and then antinodes in between. And because it's an m is equal to 1 standing wave we're concerned with, we just want to look for the case where we have only one antinode. So that means that half wavelengths that fit onto that string, I take m times some base value, where that base value is just v over 2l, I can figure out what any higher m value standing wave is. So I can just plug in a 1 for m, and I get 45.64 meters per second divided by 4 meters, and that is 11 hertz when you apply sig figs. Number 5, what are the wavelength and frequency of an m is equal to 1 standing wave on this string at the increased tension value? I'm using the same expression, but a new wave speed, so I'm not going to get the same frequency. Instead, I get a frequency that is greater. You get 26.45 hertz, which would round to 26 hertz, despite the fact that the wavelength is the same for number 4 as it is for number 5. Changing the tension changes the wave speed, which changes the frequency, as we can see when we look at the answers to number 4 and number 5. But the one thing that's staying consistent is the wavelength. The 230 hertz signal is now turned into a sound wave. What are the wavelength and period of this sound in room temperature air? So room temperature air, that's 20 degrees Celsius. If you use the full wave speed equation, you will find that the speed of air in 20 degrees Celsius, the speed of sound in 20 degrees Celsius air is 343 meters per second. So dividing that by 230 hertz gives 1.49 meters when sig figs are applied. So we have our wavelength. The period, though, is just something that is correlated to the frequency. So in other words, this sound wave could be propagating through air of any temperature, and it would have exactly the same period, so long as that 230 hertz frequency were held steady. So the period's just the reciprocal of 230. Applying sig figs gives you 4.35 times 10 to the negative 3 seconds. Number 7, what type of temperature change would cause the wavelength of the same sound to increase by 1 centimeter? So I took the original wavelength of 1.491 meters and I added a centimeter to it so that now it is 1.501 meters. I can figure out the new wave speed because I've got the frequency. I've just calculated the new wavelength. That product is going to be slightly faster than we saw for the previous question. Now I can go back to that wave speed equation. The speed of sound in air that has some given temperature is going to be 331 meters per second plus 0.600 meters per second per Celsius degree times temperature. So I can solve for the temperature and just compare it to where I started. The new temperature is 23.83 repeating degrees Celsius. So I can take that and subtract 20 degrees Celsius off, and I have a temperature increase of 3.83 degrees Celsius. Number 8, this sound's intensity is 3.0 times 10 to the negative 9 watts per square meter. How loud is it? So intensity and the loudness of a sound are related but not interchangeable. So the equation that we want is the one that will give us a decibel value. Beta is equal to 10 decibel times log base 10 of this ratio, I over I naught, where I naught is the minimum intensity that the human ear can detect. That's 1.0 times 10 to the negative 12 watts per square meter, just a constant. So I can plug in the intensity we were given and end up with 34.771 decibel, which we could round to 35 decibel because we have 2 sig figs for this problem. Number 9. This 230 hertz sound wave forms an M is equal to 3 standing wave in an open tube. How long is the tube? Assume room temperature air. So that means we can assume that the speed is 343 meters per second, not the slightly elevated one that we calculated 2 questions back. Because we have a tube with matching ends, only half wavelengths can fit into this tube as a standing wave. But because the tube is open, each end is going to represent an antinode. So M is equal to 3 is referring to 1, 2, 3 nodes for the open tube. I can plug in the frequency we were given, the wave speed, and then the mode, or M, that is 3. And the tube length would have to be 2.24 meters in order for this 230 hertz sound wave to produce an M is equal to 3 standing wave. Number 10. What would be the frequency of an M is equal to 3 standing wave that formed in an open-closed tube of the same length? So the main thing to remember here is that for the open-closed tube, you are counting the number of quarter wavelengths that you can fit into that tube. And also that means that even M values just cannot yield standing waves in tubes like this one. So I have one node on the blocked end because there always has to be a node. But because this is an M is equal to 3 standing wave, I'm just going to have one additional node there. Because this is an open-closed tube, and I'm counting quarter wavelengths instead of halves, I can use F sub M is equal to M times V over 4L instead of 2L. I've got the original length from problem number 9. I have the temperature, and I'm calculating a new frequency. This gives us 115 hertz. A laser pointer produces light with a frequency of 7.0 times 10 to the 14 hertz. 11. What are the wavelength and period of this light wave? So, just like we saw a few questions earlier, the fact that I know the frequency of the light wave means that I can determine what the period is without knowing anything at all about the wavelength or the speed at which this wave is propagating through whatever material it's moving through. All I have to do is take the reciprocal of 7.0 times 10 to the 14 hertz in order to get the period. That gives 1.4286 times 10 to the negative 15 seconds. So applying sig figs, that would be 1.4 times 10 to the negative 15 seconds. And to determine the wavelength, I need to know the speed of light. That speed divided by this frequency gives me a wavelength. And we get 4.2857 times 10 to the negative 7 meters, which is 4.3 times 10 to the 7 meters when sig figs are applied. That is the same as 430 nanometers. To go from meters to nanometers, I could just take this value, 4.3 times 10 to the negative 7, and multiply it by 10 to the 9. 12. The light is incident on a diffraction grating with 450 lines per millimeter, forming a pattern on a screen 1.8 meters away. How far apart are the first and second bright maxima? So first off, we can take what we know about this diffraction grating to figure out first how many lines you can fit into 1 meter, if 450 fit into a millimeter. And then we can take that reciprocal in order to figure out the spacing between adjacent lines. That's 2.2 times 10 to the negative 6 meters per pair of lines or between pairs of lines, but we can just take this unit to be meters. Because we're working with a diffraction grating, the expression that we're going to want is d sine theta m is equal to m times lambda. And we're trying to find not just one bright maximum, but 2. So I'm going to plug in m is equal to 1 for one of these. Then the second time around, I'm going to plug in m is equal to 2. I can determine the angle theta 1 because I have the spacing of the slits on the diffraction grating, and I have the wavelength that is still 4.2857 times 10 to the negative 7 meters from the previous question. So theta 1 yields 0.19407 radian. Theta 2 yields 0.39598. And this should also be radian. Sorry for the unit typo. I didn't catch that before. So I've got the two angles. I can now switch to the equation y sub m is equal to L times tan theta m. I'll do it once for m is equal to 1, again for m is equal to 2, and I end up with 0.35378 meters for the position of the m is equal to 1 bright maximum or bright fringe. And for m is equal to 2, it's positioned at 0.752517 meters. And we're looking for the separation between the first and second bright maxima. That's just y2 minus y1. So we get 0.398732 meters. to 2 sig figs, that is 0.40 meters. 13, would the distance between bright maxima increase or decrease if this laser were replaced by one with a longer wavelength? So we can look at d sine theta m is equal to m times lambda, and think about how changing lambda would change theta, because we are not changing the slit spacings, so lowercase d is a constant. What you'll find is that increasing lambda increases theta m. So that means that the spacing between the first and second bright maxima for the new wavelength that is described here in question 13, it would be wider. So ym increases. That means delta y would increase. 14, the grating is replaced with a single slit of width 10 micrometers. How far away would the screen need to be if the resulting diffraction pattern were to have a 10 centimeter wide central maximum? So we've gone from the diffraction grating interference pattern to the single rectangular slit interference pattern. So that means that you end up with a wide bright maximum and then bright fringes that get narrower and dimmer as you work your way out to either side. For the diffraction grating interference pattern, the bright fringes are all approximately the same width. This expression pertains only to single slit interference. W, which is the width of the central maximum, is equal to 2 times lambda L over A, where lowercase a is representing the width of the single slit. And this W is something that's kind of easy to confuse for the width of the single slit, but it's the width of the central maximum. It's also equivalent to 2 times the distance between the center of the pattern and the first order dark fringe. Because if you think about it, it's the position of the dark fringes that ultimately determines how wide the central maximum is. I know everything here except L, so that means that the slit width times the width of the central maximum over 2 lambda will give us L. And we're using the same wavelength as we used before. Both the slit width and the central maximum have to be expressed in the same units as our wavelength is expressed in. And I end up with an L that is 1.16 repeating meters. That's 1.2 meters to 2 sig figs. 15, assuming you left the screen in the same location, what would happen to the width of the central maximum if you replaced the laser with one with a shorter wavelength? So I can go to the same expression as we used in number 14. It's still 2 times lambda times L over A. So if lambda decreases, but L stays the same, and you're using the same single slit, so the same width A, that means that W is also going to decrease. So this would produce a narrower central maximum. The 7.0 times 10 to the 14 hertz laser pointer is aimed at a glass aquarium filled with water. 16. The laser is held perpendicular to the surface of the water. With what speed and wavelength will the wave pass through the water? So we need to know the index of refraction of water, which is 1.33, and how that relates to the speed at which the wave is actually moving through the water and the speed of light. And the index of refraction is defined as the speed of light in a vacuum divided by the speed of light in this material that has index n. So V is just going to be the speed of light in a vacuum divided by the index. That's 3.00 times 10 to the 8 meters per second divided by 1.33, which gives you 2.25 times 10 to the 8 meters per second. We're still working with 2 sig figs coming off of the sig figs in our frequency for the laser pointer. So that is going to be 2.3 times 10 to the 8 meters per second. And then here, lambda, that's just going to be speed over frequency. We've found the speed, divided by the frequency. And applying sig figs, you get 3.2 times 10 to the negative 7 meters, which is the same as 320 nanometers. 17. What would be the refracted angle if the laser were held 60 degrees above the water surface? So 60 degrees above the water surface, that's different than 60 degrees away from the normal. And it's the angle between the light ray and the normal that is the relevant one. So I'd have to take 90 degrees and subtract 60 out so that the angle of incidence would be 30 degrees. I have the boundary between air and water, and I didn't state this outright, but we are assuming that the speed of light in air is not different enough from the speed of light in a vacuum in order for its index of refraction to be of interest. So realistically, air's index of refraction is about 1.0008, I believe. So we're just calling that 1.00 for N1. Sine theta 1 is going to be the sine of 30 degrees. And then that's got to be equal to N2 sine theta 2, where I know the second index of refraction, but I don't know the angle theta 2. And because of the fact that this light ray is going from air, which has the lower of the two indices of refraction, into water, which has got the higher of the two, then this angle should go from a big value to a smaller value. So the fact that we get something that's less than 30 makes sense here. 18. If the wavelength of the beam shrank to 300 nanometers when it passed through the glass part of the aquarium, what is the glass's index of refraction? I know the wavelength, that is our target. 300 nanometers is 300 times 10 to the minus 9 meters. Multiply it by the frequency, which is the same one we've been working with for a few questions now, 7.0 times 10 to the 14 hertz. And that product will give 2.1 times 10 to the 8 meters per second. So not quite as quickly as the ray moved through the water, which was 2.25 times 10 to the 8 meters per second. So that tells us that the index of refraction we should get for the glass should be a bigger number than the one that we used for water. And we can use this index of refraction equation in order to confirm that. The speed of light divided by the speed that we just calculated does indeed give you something that is bigger than just 1.33. When you apply sig figs, it rounds to 1.4. 19. If you shut the laser off and held it 16 centimeters in front of a lens with a focal length of negative 30 centimeters, where would its image form? Describe the image that would form. So the focal length of this lens is a negative. That's the immediate tell that you're dealing with a diverging lens and not a converging lens. 2, if you know that the distance between the lens and the object, which is the laser pointer, is smaller than the focal distance, which is 30 centimeters, you're going to end up with an image that is shrunken, so it's reduced, it's upright, and it's virtual. So it only looks like the light rays are passing that point in space, or they're passing through that point in space. In reality, you are tracing virtual rays back to find where that image is. And this is a kind of janky, not to scale ray tracing diagram here, but I know that if the focal length is 30 centimeters, the object position should be just about half of that because it's 16 centimeters. And if you ray traced, you would find that the image would have to show up as upright, it'd have to be reduced, and it would have to be virtual. We can confirm that by using the thin lens equation and the magnification equations. So we are adding the reciprocal of the object distance, that's 1 over s, to the reciprocal of the image distance, 1 over s prime. That gives us the reciprocal of the focal length, 1 over f. And we know everything in that expression except for s prime, so we can just solve for that. And we've got s prime as negative 240 over 23. So I use 240 as a common denominator. You get negative 23 over 240 as 1 over s. That means, or excuse me, 1 over s prime. And that means s prime is minus 240 over 23 centimeters. So negative 10.4348 centimeters. Again, this ray tracing diagram is not actually to scale, but it predicted an image distance that was smaller than 16 centimeters, and I have indeed found one that's smaller than 16 centimeters. To 2 sig figs, that's negative 10 centimeters for the image distance s prime. Now to figure out the magnification, I can just take minus s prime over s. So that is two negative signs that are going to cancel out. This is positive 10.4348 divided by the object distance, which is 16 centimeters. I get m is positive 0.65. So because the magnification is a positive value, this is something that's going to be upright. Another way of figuring that out is thinking about the object distance s prime. If that's a negative, that's going to cancel this negative, and it's going to give you a positive magnification. So upright is the only option, really, for this type of lens, but we can still confirm that that should be true by looking at the magnification expression. Next, we want to confirm that it's reduced. Pay attention to the absolute value of m. 0.65 is smaller than 1, so the image that forms is going to be smaller than the object. And I skirted past this beforehand, but we've known since we got a negative image distance that the image that we're talking about here is a virtual one. So that's also something we could have figured out just by recognizing that this is a diverging lens, because that's the only type of image that lens can make. But a negative s prime automatically means virtual. And then finally 20, if you held the laser 45 centimeters in front of a converging lens and produced a real inverted reduced image 30 centimeters behind the lens, what would that lens's focal length be? So start with the thin lens equation again, add the reciprocal of the object distance, which is 45 centimeters, to the reciprocal of the image distance, 30 centimeters. And this image distance is a positive because this is a real image. The rays actually pass through that point in space instead of just looking like they're spreading from or passing through that point in space. So when you figure this out, you're going to end up with a focal length of 18 centimeters. It's a positive because it should be. Converging lenses have positive focal length. And just like before, we can use the magnification expression. Minus s prime over s is going to give a negative value this time, simply because object distances are always positives. The image distance we calculated, or that we were given, is one that is a positive value. And this is negative 0.6 repeating. So the image is going to be reduced because 0.6 repeating is smaller in magnitude than 1. The image is going to be inverted because we calculated a negative magnification instead of a positive one. And because the light rays are actually passing through this point on the far side of the lens, we know that this is a real image. That's also something that we could have surmised just by looking at the sign of s prime.